Hey everyone, and welcome. Today, we're going to break down some really core Java concepts. We're talking about how to build code that isn't just functional, but is also super efficient, really well organized, and tough enough to handle the unexpected. So let's just jump right in. So let me ask you this. Have you ever been there? You're deep into a project and you realize you're just copying and pasting the same chunks of code, maybe changing one or two little things. It feels wrong, it feels slow, and that's because it is. Well, that exact problem is what we're here to solve today. Just imagine for a second that you're in charge of a car factory, but for every single car, you have to start from absolute scratch. I mean, smelting the metal, molding the frame, building the entire engine piece by painful piece. It would be a nightmare, right? So slow, so repetitive, and if you found a mistake in one car's design, you'd have to go back and fix it in every single car you'd already built. That is exactly what writing repetitive code is like. Okay, so how do we escape this nightmare factory? Well, the first big tool we're going to talk about is inheritance. Honestly, the best way to think about it is like a family tree for your code. Instead of building every single thing from scratch, you create a new class, let's call it a child, that automatically gets all the features and behaviors from an existing parent class. And just like that, we've solved our car factory problem. The absolute biggest win here is code reusability. You write some common code one time in a parent class, say a vehicle class, and then you can reuse it everywhere. This saves a ton of time. It also lets you do cool things like letting a child class create its own special version of a parent's feature. Plus, it helps you organize everything logically. We call this an ISA relationship. For example, a car is a vehicle. It just makes sense. Now, the most basic version of this is called single inheritance. It's super straightforward. You have one child class that inherits from one parent class. A perfect example is a programmer class. A programmer is a type of employee, right? So the programmer class can inherit from an employee class. It gets all the standard employee stuff like a salary, but then it can add its own special details, like what programming languages it knows. We can actually take this idea and stretch it out into what's called multi-level inheritance. Think of it like a family line. You have a grandparent class, then a parent class inherits from that, and then a child class inherits from the parent. And here's the really cool part. The child class gets all the traits from both its parent and its grandparent. It's like inheriting your dad's sense of humor and your grandpa's hairline. And then there's hierarchical inheritance. This is where things get really efficient. You have one single parent class that acts as a kind of template for lots of different children. Imagine you have an animal class. Well, from that one class, you could create a dog class, a cat class, and a bird class. They all share the basic animal stuff, but each one has its own unique way of doing things. So inheritance is awesome for reusing code, but what if you want to think bigger? What if you want to create a master blueprint, a grand plan for how things should work? Well, that's where abstraction comes into play. Abstraction is all about hiding the messy, complicated details, the how, and only showing the user what they actually need to know, the what. Think about a car's steering wheel. You know what it does, right? It turns the car. You don't need to know every single gear and piston involved in how it does it. In Java, there are two main ways to do this, with abstract classes and with interfaces. An abstract class is kind of like a partial blueprint. It can give you some of the methods already built, but it leaves some blank for you to fill in. An interface, on the other hand, is a pure blueprint. It's a contract that says, hey, if you use me, you have to build these specific methods yourself. The really big difference here is that a class can only have one parent, but it can implement multiple interfaces. And that's how Java lets you build some really powerful and complex designs. Now, let's say you've designed a class and it is just perfect. You don't want anyone else coming along and changing it. For that, you use the final keyword. Think of it as putting a big, heavy lock on your blueprint. When you make a class final, no other class can inherit from it. When you make a method final, no child class can change it. It's all about control. Okay, so you've done it. You used inheritance and abstraction, and you've built this elegant, efficient, beautifully organized program. It's a work of art. But then, someone runs it, and they try to divide by 0, or they look for a file that doesn't exist. And bam, your whole program crashes. All that beautiful design means nothing if your code is too fragile to handle the real world. This brings us to our second big topic for today, exceptions. An exception is just the technical name for when something unexpected goes wrong while your program is running. It's your code throwing its hands up and shouting, "Houston, we have a problem." And if you don't have a plan for these moments, your program just stops. dead in its tracks. But thankfully, we have a solution, and it's called exception handling. This is basically a safety net you can build into your code. So instead of letting a random error bring down the entire show, you can catch that error, deal with it gracefully, and let the rest of your program keep on running. This is what separates flimsy code from truly robust, reliable software. So how does this safety net actually work? Well, it's a simple 3-step process. First, you wrap any code that might cause trouble in a try block. This is you telling Java, okay, give this a shot, but be ready for things to go sideways. If an error does happen, the program immediately jumps to a catch block. This is your safety net, designed to catch that specific type of error. And last but not least, you have the finally block. This is the cleanup crew. It always runs, no matter what, to do things like close files or clean up resources. And what kind of accidents are we talking about catching? Well, here are some of the usual suspects. That arithmetic exception? Yeah, that's the classic tried to divide by 0 error. A null pointer exception is what you get when you try to use an object that doesn't actually exist yet. And array index out of bounds exception, that's like trying to find the 6th step on a 5-step ladder. It's just not there. The names might sound a bit technical, but the ideas behind them are pretty simple. All right, let's pull this all together. What we've really done today is build a brand new toolkit for writing much, much smarter code. We've got inheritance, which makes our code reusable, so we're not constantly reinventing the wheel. We've got abstraction, which keeps our code organized with clear, easy-to-understand blueprints. And we've got exception handling, which makes our code robust, strong enough to survive whatever the real world throws at it. When you start combining these ideas, you stop just writing lines of code, and you start engineering elegant, resilient, and truly professional software. You have the blueprints now. You have the tools. So the only real question left is, what are you going to build first?